So welcome back, everybody, to the continuation of today's conference workshop. Our next speaker, Katrin Wehrheim, uses they, them pronouns, is an anti-fascist revolutionary by calling and a global analyst by training. Applying this training to questions in low-dimensional topology and symplectic geometry while appeasing the power structure with women in math outreach activities rather than addressing the real problems, led them to hold positions at ETH Zurich, Princeton University, IAS Princeton, MIT, and UC Berkeley. After gaining tenure, despite losing the battle for proofs in symplectic geometry, I'm sure there's a story there, their main learning and doing has been on matters of fascism, racial capitalism, genocide accountability, reparations, and justice at large. More recently, their identities are combining into mathematics education to counter oppression. So Katrin, please go ahead.
Thanks so much. I'm excited to be here. Thanks for making this possible. Yeah, and this is a stretch, as Tyler said. I have to talk out of at least 3 sides of my mouth. It's an interesting challenge. So I was really pondering what makes my mathematics queer, what makes my life queer. And I was realizing that while I came out only after getting a tenure track job, really my queerness comes from birth. There's no good word in English that I found. The word in German is Querkopf. It's a sort of queer as a not straight head. Some people would call it contrarian. I think of it, I perceive it as somebody who sees clearer and will call bullshit and not go by just what's assumed to be, standard process, but will go their own path. And so I think my queerness and my non-binary identity, or maybe the fuck gender identity, are really corollaries of my being born a Querkopf. I was also born an anti-fascist in Germany with quite a heritage. And I can tell people more if that becomes a bigger topic. I want to take you on a bit of a journey to where I'm at today. There will be a lot of heartbreak. There will be my math heartbreak that has something to do with the proofs in symplectic geometry. There will be what I've seen about how math interacts with humanity these days, mainly in the US, from things I've seen organizing in the streets. And eventually there will be hope. I promise hope. So there will be hope that math might actually contribute towards bending the arc of the moral universe. And for me, that mainly happens in classrooms today. So there will be an invitation to joining that idea of using mathematics education as a counter-oppressive practice. So I'm going to slide down to the math heartbreak situation. So it's 2008. I've been out for a year or two. I'm kind of done with breaking hearts, getting my heart broken. I'm ready to do some math again. My math kind of happens in low-dimensional topology and symplectic geometry and the connections between them, where we prove amazing things about really very geometric things, about getting balls into cylinders or not, which birthed symplectic geometry, and about which topological 4 manifolds can you put a smooth structure on. And those proofs go via some geometric PDEs. So there's some geometric PDEs for you that I'm entirely not going to explain. And so what we're doing with them is we're looking at the solution set and we're quotienting out by some equivalence relations of obvious symmetries, and then we're going to need to compactify the whole situation. And then we kind of need to count them, or we need something that's like a fundamental class. So these fundamental classes used to be called virtual. During my PhD, I realized just how virtual they were. I could virtually not understand a thing. I was assured that this would be sorted out by the time I needed to actually use them. So this is the story of how that got sorted out. So first of all, these fundamental classes were actually constructed in many examples where wiggling with the geometry does the job, right? And then by the time I became sort of a grown-up mathematician, there were at least 3 abstract theories that explained to us what to do when wiggling the geometry wasn't enough. So these abstract theories really sort of think about the moduli space as the 0 set of a section or a function. So I want to give you a vague idea what that looks like when I get rid of the PDEs, when I get rid of the quotients, when the M itself already is compact. In fact, we're going to look at the case when the M itself is just a point. Right? So that's my compact moduli space here. And there's various ways in which that could be cut out, right? So it could be cut out by the function f of x is x, right? Then my, let's see, right? That's where M is. It's the origin, my 1 point here. Nice. That seems like a very nicely transversely cut out solution. We'll declare that to be the fundamental class of this space. All right, so far so good, I hope. Now, what if I think about the function x squared, right, that cuts out the same space, but it's kind of a double 0. So, right, should it count twice? What should we do, right? And so our business is we kind of perturb, right? So we could perturb, however, we could perturb this way, or we could push the whole thing up, right? The bottom one has 2 zeros. The top one has none. Which one should it be, right? And so it turns out that if you count this with orientations, it should be 0. All right. And so now you can guess how this keeps going, right? So the game with x cubed, in our world, we like to perturb so that the 0 is transverse, right? And so then that again just becomes a point. And that was the absolute toy example, right? The thing I'm not going to talk about is how I got involved into this, because we're already going much slower than I was supposed to. So I'm just going to scroll through that. And tell you about the virtually true theory that was literally called virtually true in all my surroundings and by massive leadership in the field. And by the time I was a more adult mathematician, I was trying to publish papers and I was told I should use this virtually true theory to simplify all my work. I still virtually understood nothing, so I called for help. Tuza McDuff answered my calls, and we've been collaborating on making sense of this ever since. And so here's a little bit of the sense that we made, right? So what is the idea of these nowadays called true theories? It's amazing. You call out somebody's bullshit and then the virtually true theories become true just by virtue of having been criticized. So the theory is that instead of just one function cutting out your moduli space, you have a couple of functions, right? So as long as you're locally the 0 set of some continuous, maybe differentiable, maybe smooth, debatable, yeah, let's assume smooth sections. So yeah, your moduli space is kind of the union of a bunch of 0 sets with some identifications on overlaps, right? Well, clearly you're going to need some kind of compatibility on overlaps. The problem here is like when I draw this, it looks like everything is embedded in the plane. Yeah. It entirely is not. Like the key here is that this M bar is really just the union of the zero sets. The ambient spaces on which the functions happen would, how they fit together needs to be in this compatibility. Right? So, all right. So we have this local descriptions, and so then the idea, right, for making a nice representation of a fundamental class is, well, manifolds have fundamental classes, and so maybe we're going to do the same thing that we did before. We're going to perturb each of our sections slightly. Hope that the overlapping condition still glues that together somewhat. We're going to preserve the compactness somehow in this perturbation. And we're also going to preserve the fact that the resulting topological space is Hausdorff. Right? If we can do all of that, then this glued together thing here is a manifold, which has a fundamental class. And very roughly speaking, we take its fundamental class and declare that to be the fundamental class of M bar. Maybe we're going to call that the virtual fundamental class. Right? So that's the idea. Right? I understood virtually nothing. So Dusa needed to explain all of this to me. And like every now and then, right? My bullshit detector was very active in those times. I wouldn't understand. And so she would try to explain, and I still wouldn't understand. And eventually she got, maybe a little tired of that and said, why don't you read the paper? So I read the paper, right? Compatibility comes from the fact that conjugacy classes of maps have a well-defined composition. Preserving compactness comes from the fact that infima of positive functions are positive. And Hausdorffness comes from the fact that quotients of Hausdorff spaces are Hausdorff. So this is the awakeness test. Anyone want to call bullshit on any one of these? Right? I know folks have been talked at for a long time, and this is a lot I'm throwing at you. These are all things I would fail somebody over in a qual in differential geometry. They're patently wrong. And these are not local mistakes. Trying to fix any one of them causes a 100-page paper. And so I'm not going to give you those arguments. I'm going to show you something even more disgusting, maybe delightfully disgusting, right? Quotienting things out is really not a good idea. Here is one of my least favorite topological spaces. It's just the real line with half space attached to it. If you construct that as a subset of the plane, fine. But if you construct that as a quotient space, it is not metrizable. It's not locally compact, it's not metrizable. And so for us, that's a problem because we can't talk about perturbing just a little bit. Yes, that's what people do. Right? And so this whole area is really one in which unconscious beliefs over and over derail correct mathematics. So, as John Stewart said, chaos on bullshit mountain. That was very liberating for me. There was a clip that I played over and over again when this first broke. It was hard, unspeakable violence happened. Never physical, but it did destroy lives and careers and relationships, and it destroyed my interest in really having a career in this field. In particular, right, I sort of went and jumped on a different ship. I jumped on the ship of polyfold theory, in which I can explain to you why the ideas should work, right? except polyfold theory was announced in 2005. I've been teaching it to students for about 10 years. And the foundational papers that they would need to really publish their PhDs and good papers are still not there. They've been promised since 2006. I don't know that they're coming out. Yeah. So I think the ship floats, but it's not getting into a harbor. Right? So that's my math heartbreak. To make matters worse, what really, really pissed me off when I woke up to that fact is how many years of my life and how much energy and how much funds I had spent on an entirely academic question. When people were dying and being violated right outside of the door of my house, often with my implicit involvement. And so come 2016, I started working out in the larger world. But if you could slide the slides over to the right, yes, that one, math versus humanity, right? So question for y'all, and I would love you to just throw something in the chat. It could just be one of the numbers. What would you say are the biggest problems that mathematics has created? Not just what are the biggest problems in the world, but what are the biggest problems that mathematics has some responsibility for? Yeah. Is mathematics responsible for racism, homelessness, police violence, climate breakdown? Algorithmic discrimination, indeed. Yeah. Highly recommend Cathy O'Neill's Weapons of Math Destruction. What else? Fiscal austerity, yep. Right. A lot of bad financial decisions come from people who claim to model reality with formulas, right? And so maybe here's do I actually want to get into this story? I will tell you a very, very brief version of this story. If you slide down a little bit, I was working with unhoused folks in the village of Oakland who were building their own housing, little sheds on public land. And their financing came through a fiscal sponsor who was channeling donations to them as a 501c3. And so some accountant needed to have spreadsheets to figure out how much money they could spend to buy more building materials, right? And so when I worked with them, there were every now and then it's like all buildings stopped, there was no money. Although donations were coming in, it's like somehow money had vanished. And so these badass organizers who didn't take no for an answer ever, sat down with the accountant. I went along, fortunately. The moment they were they saw a spreadsheet, the moment they were like confronted with numbers, their entire badassness evaporated and you could tell them anything. These folks were also fantastic at math in their head. They computed where all the bars, where all the lengths, the angles, these are incredibly smart people. The thing, none of them, neither the educated accountant nor the badass organizers noticed that there was a problem with the spreadsheet where the fiscal sponsor was usually the sender, but then sometimes it was the receiver. But somehow the sums that were being put on were all added instead of subtracted when there was or they were all minuses, right? And so There's one crucial sign mistake because something went the other way here. That should have come with a different sign, and instead of a minus 5,000, this should have been a $0 situation. Right? So it took a professor at UC Berkeley to have the sense of entitlement of that spreadsheet making sense. Yeah. And then it took my extreme pedagogical skills that I built up to that point to manage to communicate this in such a way that the problem was actually corrected. So I thank Chaos on Bullshit Mountain and Symplectic Geometry for teaching me not to just tell people that they made a mistake, but for finding a very, very intermediate way of guiding them to that realization. Yeah. More people's houses got built because I got that bullshit detection and bullshit communication education. All right, time for some hope. So moving on over to the right again. Right, I want to make the case that it is not just possible for math, but it's actually imperative for math to busy itself with bending the arc of the moral universe, because a lot of the destruction of settler colonialism, capitalism, racial discrimination, algorithmic discrimination has been made by math. Yeah, we have reparations to make, and in part that means repairing communities by throwing the power of mathematics on the side of justice. I've learned a lot from a lot of people. There's lots of fantastic links in those documents that I highly recommend you follow at a quiet time. Given the amazing participation in the chat, I'm not going to ask this question. But if you're awake and you want to throw something in, please do that. Yeah? What do we want? The street level answer to that is justice. How are we going to get it? People power. If we don't get it, shut it down. That's what's being chanted at UC Berkeley in the big strike right now. What do we want as mathematicians, right? As mathematicians and humans, as queer mathematicians who understand oppression in a different way than most of our straight colleagues. Right? And let's grasp for the big stars, right? So, and then let's think about how we're going to get there. Yeah. And so I want to present to you the little case study, small little case study of the ending of the division of the Germany, and also really the ending of the Cold War. Right? This is a 10-minute segment in my linear algebra course. I show the videos, I cry every time. I think it's really important to cry in front of your students every now and then. Kind of helps. Right now, I just want to point to the math content of this. The math content is in these little graphs. Right? So how did the Berlin Wall fall? Yeah. Very short story, I would say, is that there were peace prayers over decades in the Leipzig Nikolai Church. And one Monday, September 4th, somebody suggested, hey, after the prayer, how about we walk around town and chant, "We are the people." 2 months later, the world changed. 2 months later, the wall came down. Yeah. And I got to be there and hammer out my own piece. Yeah, my most cherished possession. And so the first Monday, that was 1,000 people. The second Monday, we don't have data. The third Monday, maybe it was 1,500. It looked number-wise like not a lot was happening. And then suddenly it exploded to a place where, right, a government couldn't lock up its own people any longer, right? So what's happening here is, of course, exponential growth, right? So if you take the logarithmus naturalis of this function, that looks a lot more linear, right? So that means there's some exponential growth here. And there's a really helpful graphic I find, if you scroll further down, right? If we set ourselves even just a very modest goal, we tend to expect to get there linearly. Yeah. But most change work, if it works eventually, actually needs to avail itself of exponential growth, right? And so the exponential function goes differently, right? And so there's this whole area of disappointment where the exponential function is much lower, right? And only after some inflection point do you have the amazing disruptive power of exponential growth, people power, right? So how do we make that happen, right? So I think in order to get a change movement going, right, like the fall of the Berlin Wall, we need a low engagement threshold. It makes it easy for people to engage. It needs to be infectious. We know all about that at this point. But once people get involved, it needs to be sustainable. And it needs to have a high ceiling. And I would say an audacious goal of really changing like something substantial about humanity, right? And I would like to argue that mathematicians have something that has a lot of potential for these things directly at our disposal. Right? How do we engage in change work on top of our busy schedule? How about we bring the change work into something that we're doing already, right? Most of us are teaching, right? And so for me, the most sustainable way of making change is to do it in the places that I am already, right? Where I have power, where I have 700 students next semester. But even when I have a seminar with 3 students, right, I can teach values even by basing things on accessibility principles. There's so much we can do in the classroom that our students are eager to learn from us, right? They're looking to us also as adults who are showing them how to adult, right? So we can bring so much in. I think it's infectious, low engagement threshold, right? You can start bringing some things in, and the sky is the limit, because your students are going to teach other people who are going to teach other people, right? So teaching is a place to make change, yeah. And we've already heard from Joseph some calls on things. I have the same one of the same books to recommend. I also have books from K through 12 spaces to recommend. My main recommendation is start doing something. Yeah, set a goal for yourself of how you want your teaching to affect your students outside of the classroom. Yeah, and then just try something, observe what it does, and adjust to get closer to your goal. Yeah. And right, I'm looking at the time. So I want to just briefly tell you, so there's sort of really 3 perspectives in which you can think about teaching math and social justice, right? There's the with, the about, and the for perspective. With, I would call that the usual diversity, equity, inclusion thing. Plenty of resources, yeah. Lots of people talk about it. We should all, obviously we need to do it, right? There's the about, where we talk about social justice, where we use mathematics to analyze social justice issues. And there's the for perspective, which is really where my heart is. And that I haven't found very much about. So this is something I would like to invite everybody into conversation on. If you scroll a little bit further down, this little paper that's listed there with a number of authors that I forget, talks about this in terms of we teach for social justice when we're aiming to emancipate our students and ourselves from a deeply unjust and unfair world. Right? So when I do that, I really have the whole humanity in my goals when I'm in the classroom. And I found that that makes it so much easier to figure out how to do all the accessibility requirements, right? Like there's all the, oh, how is, this student is going to be uncomfortable with that. This is not accessible for them. Am I going to do group work or not, right? What with the one Black student in a group of white kids? Am I going to do group work? How am I going to make groups, right? The DEI perspective, this is really hard. From the teaching to counter oppression perspective, it's no easier, but I'm less confused, because for me, it's very clear that we need group work, and I need to teach people how to treat each other with respect, how to hear everybody, and how to lift up all the voices and really pull from everybody's expertise, right? So no easier, but I'm much less confused about what I need to do in the classroom, right? Which is I get to shift the culture in my classroom, right? And I have a bunch of examples here of how I've been managing to do that. This is entirely work in progress. There's one book that entirely does not talk about social justice, but which I found the most influential for my own practices, just called Building Thinking Classrooms. Follow those links, Google that. There are podcasts and little, quick summaries to be had. If you're frustrated by your teaching, or if you're frustrated by the amount of what gets through from your talking to your students' brains, this is the book for you. The introduction will tell you all you need to know. This differentiating between studenting and learning behavior, and the differentiating between mimicking behavior and thinking behavior really, made so much more things clear to me. Right? And yes, we can shift it. Right? I've been teaching from this perspective. I've been teaching grad students to teach from the perspective of centering thinking in the classroom. And I think pretty much no matter what your big change goal is, maybe making capitalism work better, maybe, right, like political this, political that, teaching students to think and solve unsolved problems is going to contribute towards that. All right. So I think it's a very bipartisan goal. It's also much more mathematical. So it should not be a problem to convince your department that that's a good thing if your students think harder and think more mathematical. So, and my pitch is that that is a way in which we can make amends as mathematicians to the world by empowering more students, more future mathematicians to think about the mathematics before they apply it, right? Hopefully they'll build fewer weapons of mass destruction that way, right? Think about rules before you apply them. So with that, I would love to hear your thoughts, and I'll also throw my email in the chat because I'd love to, connect with people who want to engage in that practice.